Hi guys, and welcome to another video. In this week we're going to be talking about the idea of probability and randomness. But before we start that, I just wanted to say well done for finishing the first intro series where we do the basics of Python programming. I hope you found it interesting, and we did cover a lot of content in a very short space of time, so don't worry if you can't remember everything. There's going to be plenty of opportunities to practice the things that you've learnt, and we're not expecting you to have just memorized everything, so don't worry about that at all. I also wanted to say that programming is not easy, especially at the start, and there have probably already been times where you felt a bit frustrated, like you didn't understand something and it's not working and you don't understand why. That's completely normal. It happened to me a lot, still happens to me sometimes. But I just wanted to say that the payoff is really, really worth the effort. And if you stick with it now, you will have a moment where it just clicks and everything starts to make much more sense. And you realize that this tool will allow you to basically do anything you want. I also just wanted to say that coding is a creative process. It's about solving problems the way that you want to. So don't be afraid to just try stuff out. We've made these tutorials where there's kind of pre-written bits and sections where we ask you to write your own bits of code, but don't be afraid at all to just make a new cell and start trying some things out, experiment, and just have a go. Because that's really how you learn. It's just by through experimentation and just kind of questions that pop into your head and just seeing if you can answer them yourself. So with that said, let's move on to the topic of this week. So what is probability? Well, you've probably done some probability at school, and you have a sort of rough idea in your head of what it might be. So you probably know that probability is used when we talk about sort of events in the future that we're not certain about their outcome. They might be one thing, there might be another thing, one might be more likely than the other, and we kind of want to talk about these uncertain events that might happen. Now that's really, really important when we're talking about data science, because the whole study of data science is all about trying to understand the probability of events that we don't know about in the future, right? So in a typical data science problem, we look at some past data and we say, okay, well, given that past data, what outcomes do we think are likely in the future? So for example, if you're working at Amazon, the past data might be, what are all the products you've clicked on? And we want to say in the future, well, what are you most likely to click on next, for example? So that's an uncertain event, and we need the language of probability to be able to describe those kind of situations. So just a quick kind of recap of some basic idea of probability. So we can basically assign a number to a future event, where 0 means that event is completely impossible, 1 means that event is completely inevitable, 0.5 means that that event is completely 50-50, like it may happen, it may not, and there's completely equal chance either way. And it's kind of a sliding scale between that, right? So, 0.99 means it's really, really, really likely, but not 100% certain. And conversely, 0.1, 0.001 means that it's really, really unlikely, but it could still happen. And the kind of meaning of this number is, if I repeat that event many, 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 many times, what fraction of those times would I expect the thing to happen? So that's a bit abstract. Let's take a specific example. So here we're talking about drawing a card from a regular deck. So that's got 52 cards, and so 13 are spades, 13 are hearts, 13 are clubs, 13 are diamonds. So there's an equal number of all of these three suits. So if we draw a random card, what is the probability that that card is a heart? Well, it's going to be 1 in 4, right? Because there are 4 different groups and they're equally likely to be chosen. So the probability that we have one of those is just going to be a quarter. And that means if I repeated that 1,000 times, so if I draw a random card, put it back in, shuffle them up, drew another random card, if I did that 1,000 times, I'd expect that roughly a quarter of all those times I would draw out hearts. So that would be 250 times we'd expect, roughly. It might be a bit more, might be a bit less, but it's going to be something around 250. It's not going to be 10, it's not going to be 900, it's going to be close to 250. So in this first exercise, we are just going to basically simulate the idea of drawing a card from a deck. So we've got exercise 1 here, which is look at the graph below, and you'll see in a minute what the graph is. So let's just talk about this first cell. So what are we doing here? We're going to import NumPy as NP. So hopefully you saw NumPy in the last tutorial. That's just a module that we can use in Python to do numerical things, numerical Python. And we're also going to import matplotlib.pyplot as PLT because we're going to be plotting some graphs. This %matplotlib notebook here is just to tell Jupyter that we want to make an interactive notebook. And here we're just setting some print options, so you don't need to worry about this too much. This basically just means when we print NumPy arrays, we don't want like loads and loads and loads of digits of precision. We just want to kind of get a feel for the array. So don't worry about that too much. So we'll run that cell. We'll run this cell as well. As I say, you have to run this matplotlib notebook thing twice for some reason. Not sure why, but you just kind of have to do that. Okay, and now we're going to make graph 1. So we're going to run this cell as well. So from scripts.lesson1, this is just some code that I've written, so you don't need to worry about that. It should just work. Okay, so what we've got here, we've got this graph where if we click select a card, we're going to basically randomly draw a card from the deck. So this time we've got a 6 of diamonds, and you can see that we've got a count of 1 in the diamonds column. Do it again. Okay, we've got a hearts, and again, oh, we got a clubs. Oh, sorry, that wasn't hearts, that was a spades. Spades, clubs, diamonds, we haven't got hearts yet. Another diamond, another diamond, another club, another spade. There we go, and we got a heart. And you can keep clicking this lots and lots of times, and you'll see sort of how the distribution tends to level up. So have a play around with that. Make sure you understand that concept, because that's not really what we're going to be talking about today. So, okay, so hopefully this situation was kind of understandable. You've hopefully seen something similar at your math school. You have like, a set of different outcomes, and there's a different number associated with each one of those, and we have a kind of probability for each one. So in this case, there's a quarter probability that it's spades, a quarter that it's clubs, a quarter that it's diamonds, a quarter that it's hearts. And this is what's known as discrete probability. And now the word discrete basically means something that comes in distinct lumps or groups. So there are 4 distinct suits, and that means we're in a situation where we're describing that by discrete probability. So we can assign, okay, well, this outcome has this much probability, this outcome has this much probability, and so on and so on. And that is the case of discrete probability. But what we really want to talk about today is something else, and that is called continuous probability. Now, this is something that you may not have seen in your maths class at school. It's a slightly more tricky concept, but the idea is basically this. So the word continuous essentially describes things that don't come in distinct lumps, but have a kind of flowing quality to them. So for example, the amount of water you have in a cup is a continuous quantity, right? So you don't have 5 water or 10 water, you have, any amount of water measured in whatever milliliters. You could have, 500 milliliters, you could have 501 milliliters, you could have 510.0000055999771 milliliters. You can have any continuous amount of liquid. And that's the idea of a continuous thing. So lots and lots of things that we might want to study are continuous. Often when we're talking about probability, we are talking about a probability of some continuous quantity. So let's take an example, right? So you're standing between 2 walls that are separated by 2 meters. So we're going to put one wall at x equals 0 and one wall at x equals 2. You then take a tennis ball and you throw it at one of the walls. It bounces back and forth between the walls and then slowly comes to a stop somewhere in between. So how can we describe the probability about where the ball stops? So there's a few things here. The first thing that might come to mind is, well, there's nowhere in between these walls that's particularly special, so it has an equal chance of stopping anywhere. And that is true, right? We haven't said anything special about this wall. I mean, you know, if it was on a slope or something, we might expect it to stop in one corner, but we're assuming it's perfectly flat. So there's a completely equal chance that it stops anywhere between x equals 0 and x equals 2. What if I asked you, what is the probability that it stopped at exactly halfway between the two walls? Well, that would basically be 0, right? I mean, there's essentially an infinite number of places that it could stop, and sort of halfway is just one of those infinite places. So surely it must be 0, because it's infinitely more likely that it would stop somewhere else, right? I mean, it could stop at, you know, 1.000000001 meters, which would just be a little bit over halfway. So the probability of it stopping at exactly halfway, if we had a ruler with perfect precision, would be 0. Okay, so what if I asked you, what's the probability that it stops in the first half? That is from x equals 0 to x equals 1. Well, that occupies half of the space, so maybe it's a half. And that's right. Okay, so this is all, you know, a bit arbitrary. You're asking me, you know, you could ask why am I asking you these questions? Well, we would like to be able to kind of describe this situation very precisely, okay? And the way that we do that is by using something called the uniform distribution. Now, the uniform distribution tells us that if we have kind of 2 points and the probability is equal to choose anywhere between those 2 points, then we can't really say that any one of those points has a positive or has a non-zero probability of being chosen. All we can say is that any given interval has a non-zero chance of being chosen. Okay, and the way that we can kind of do this is we can say, well, the probability that it's within some place, say from x equals 1 to x equals 1.5, is the distance of that interval, so in that case it's 0.5 meters, divided by the total interval length, which in this case is 2 meters. So we've got a little bit of maths here that says the probability that the ball is between points A and B, where B is bigger than A, is B minus A divided by 2, because that is the interval length. So what's the probability that the ball is somewhere between 0 and 2, so i.e. it stops anywhere, somewhere in the interval? Well, that's 2 divided by 2, which is 1. So certain, it's absolutely certain that it will stop somewhere. Okay, that makes sense. What's the probability that it's between 1 and 2? Well, that's going to be 2 minus 1, which is 1 over 2, which is a half, so 0.5. Sure, that makes sense as well. So we've occupied half of the interval there, so the probability is half. And so on, some more examples here. So a question for you here is, what is the probability that the ball is between x equals 0.3 and x equals 0.7? Okay, so given that, the first little coding exercise here is to write a function that takes in, sorry about that wasn't actually the right answer, just in case you're wondering. It takes in 2 places, A and B, and tells you the probability that the ball lands between these 2 points. Okay, so you're going to need to write a little bit of code here, and I want you to write a function that returns the answer. So it tells you what is the probability that it arrives between A and B, where A and B are 2 numbers that are between 0 and 2. Okay, so once you've written your code, go ahead and run this cell here. Well, first run that cell, and then run this cell here. So I'm just going to run this one. So this currently is returning nothing. And then if you run this one here, this exercise 2 test is going to test your function in a number of different scenarios to see if it's correct. So if I just run this here, right now it's saying your function is not returning anything, so make sure you use the keyword return. So yeah, that's fine because actually we haven't written anything yet. So if you go ahead and write something here, it'll test whether you have got that correct. So actually I'll just do a little example. So if I just return 5, it's going to say your function is producing the wrong output for one or more of the tests. Try taking another look. So that's not the right answer. So you just got to come up with the right answer here. Okay. So the uniform probability distribution function. Okay, so what is this? Well, we can basically visualize the probability of being between 2 points A and B as being the area under a rectangle where the rectangle height is 1 divided by the total interval size. So in this example, our total interval size is 2. So we're basically saying we want to the probability that that the ball lands between point A and point B is going to be what we can look up here is going to be B minus A divided by 2, or rather B minus A times a half. That's exactly the same thing. So, you know, dividing by 2 and multiplying by a half are exactly the same. So essentially, you can think of it as a rectangle of height a half with a point starting at A and a point starting at B. So that maybe isn't the clearest description, but let's have a run of this graph and take a look what I mean. Okay, so you can see here that we've got a rectangle that has height a half, and currently it's at point A is at 0.2 and point B is at 1.5. So if we move around these sliders here, you can see that the area of that rectangle is changing, and that tells us the probability that it's between these 2 points. So if I put A down to 0 and B up to 2, you can see that the area is now 1, right? Because we know that it must stop somewhere in this interval. Whereas if I take B down to 1, then we've got the probability that the ball is between 0 and 1 is now going to be 0.5 or a half. Similarly, I can move this one up here and move this one here. Again, the probability is going to be a half if I can get the stuff in the right place. So you can kind of think of this probability as, so the probability of being between 2 points A and B is just the area of this rectangle, which has a height of a half. And there we go. So that's the idea of the uniform probability distribution function. So the distribution function is essentially this line here, and the area under it between the 2 points gives us the value of the probability of being between those 2 points. Okay, so that's a bit of a strange idea. You might ask, well, what is the point of that? It seems a bit contrived. Well, it's actually pretty useful, and we'll see why soon. And just a quick point here. So we can describe this function by this mathematical statement, okay? So if we have a total interval A, B, so that means in this case, our interval starts at 0 and ends at 2, then the probability distribution function, or probability density function, is defined as 1 over B minus A for x between A and B and 0 everywhere else. So that means if x is between 0 and 2, then the probability has the probability density function has a height of 1 over 2 minus 0, or 1 over 2, or a half. And if it's outside of that, it's 0. So you can see here this line drops to 0, and if you're outside of that, then it's just 0 everywhere else. So if x is not between A and B, then the value of the function is 0. And then what I'm saying is the probability of being between 2 points is just going to be the area under this curve between those 2 points. Slightly confusingly, I've called them A and B here and A and B here. So in this case, I'm talking about the total interval length. So this A is 0 and this A is 2. So this is the total interval. Whereas this A here and this B here are just free floating, and they could be anywhere inside that interval. I hope that's not too confusing. That was a bit of a mistake on my part. Okay, so in Python, we can also generate uniformly distributed random numbers. Okay, so the way that we do that is by using this NumPy module called numpy.random. And so let's take a look at this example here. So here I'm setting a value of a, which is 0. I'm setting a value of b, which is 2. And I'm setting a value of n, which is 20. And a represents the interval start, b is the interval end, and n is the number of random numbers that we want to generate. And now if we call random numbers equals np.random.uniform a, b, n, what that's going to do is it's going to create for us an array of length n, where each element of that array is a random number between a and b. Okay, so if I run that one here, it says, okay, here are 20 random numbers uniformly distributed between 0 and 2. And we can see we've got a bunch of 20 numbers here, which are kind of random numbers, and they're all between 0 and 2. Okay, so let's just take another look at this just in a bit more detail. So np.random.uniform, what's happening here? So np, that is the NumPy library, which we imported at the start. So we said import NumPy as np, so that's this thing. And then we're doing np.random. So random is a module within NumPy that's going to let us generate random numbers. So we're doing np.random, and then we're doing .uniform, which means we want to generate uniformly distributed random numbers. And then we're opening up brackets because this is now a function. And what we're passing into that function is a, the start of the interval, b, the end of the interval, and n, the number of random numbers to generate. So you can go ahead and change these numbers around if you want, see what happens. Hopefully that's clear. And of course, in this line, what we're doing is we're creating this array and we're assigning it to this variable called random numbers. So random numbers now is this array that got returned here. So you can see we're printing random numbers and we've got this here. So this is now the random numbers that we generated. Great. So we can also plot these random numbers using a histogram. So if we run this cell, we are going to get a histogram, which is basically going to count for us the number of random numbers that fall within a certain interval. So what we're doing here, again, we're setting the interval start, the interval end. This time we are going to generate 2,000 random numbers, so quite a few more this time. But again, we're just doing this thing where we're assigning all of these 2,000 random numbers to this variable. Okay, then we're going to make a new matplotlib figure. So if you remember from the matplotlib notebook, the way that we do that is by doing plt.figure, open close brackets. And what we've got here is plt.hist, which is the pyplot function to make a histogram. Now, we did histograms in the last matplotlib video. So what we do here is we put in the random numbers. So this is a random array of length 2,000 of all these random numbers between 0 and 2. And then we're going to do 25 bins. So we're going to basically split that interval up into 25 groups and count the number of random numbers that fall into each one of those little mini intervals. And then this thing here, density equals true. So one option that we sort of could have done instead is just have the raw number of counts that we have in each little mini interval. So we've created lots of random numbers between 0 and 2. And let's say there's, 100 that are between 0 and, whatever this is, 0.034. So then what we'd have on the y-axis is the actual number. So we'd have 100 up here. But what we've got with density equals true means that we're not actually interested in the raw number of counts that we have in that interval. What we're really interested in is the density of counts that we have in that interval. So what that means is you can kind of think of that as the what you'd get is the kind of the probability of being of actually ending up in this interval would be the value that you have here multiplied by the interval length. So it's basically the it's kind of more of a density, a probability density, rather than a number of raw counts. Okay, so if we run this cell here, we're going to get another kind of thing out here, another distribution like this, and the little exercise for you to do is to just change the number of random numbers that you're generating, so change this n, and also change the number of bins that you're creating, and just basically see what the effect on the histogram that has is. Okay, so that's useful. Now we're going to move on to another probability distribution. So that one we just did was the uniform probability distribution. Now we're going to move on to another one called the normal distribution. So consider a situation where you measure the height of a random person in the population with a really, really precise ruler. What is the probability that this person has a height of exactly 1.7 meters? Well, again, like the situation with the ball, the probability of having a height of exactly anything is 0, right? Because we're dealing with a continuous quantity. All that we can say is there's a probability that a person is between two different heights. So we can say, well, what is the probability that are between 1.7 and 1.8 meters? Well, that has a probability that is definitely not 0. Now, this idea of height is one that kind of many different examples follow, where there's this idea that there's kind of an average height that lots of people are sort of quite close to. Then there's a few kind of extreme people that are really, really tall, and a few extreme people that are really, really short. And as you get taller and taller, the number of people you're going to find are much, much lower. And as you get shorter and shorter, the same. And this kind of thing is typically well described by something called the normal distribution. Now, the normal distribution is defined by two parameters. The first of these parameters is the distribution mean, which has this little Greek symbol mu, and the distribution width, which has this little Greek symbol sigma. Now, the mean mu tells you the kind of average or the mean or the center of that distribution, and then the distribution width tells you basically how likely it is to find someone who's quite far away from that mean. So in the example of height, we could have a distribution mean of 170 centimeters and a distribution width of maybe something like 10 centimeters, right? What that means is basically, you're fairly likely to find someone between 1.7 and 1.8 meters. 1.8 and 1.9 starts to become quite unlikely. 1.9 plus becomes really unlikely, and so on and so on. And the same in the other direction. Okay, so the probability density function of this distribution is described by this mathematical equation here. Now, you don't need to worry too much about what everything means here, but I will just quickly describe it. So we've got this thing out here, this fraction, which is 1 over sigma, the standard deviation, multiplied by the square root of 2 pi. So you might have seen pi before, it's that number that goes 3.14159, whatever it is. And then we're multiplying that by e, which is another number, which is 2 point something, 18 maybe, 81, I can't remember, to the power of minus x minus mu squared over 2 sigma squared. So e is a number and we're raising it to the power, so you know how you can do like 2 squared or 2 cubed. What here we're doing sort of 2 point something to the power of another number. So that describes the probability density function. So we don't need to worry too much about what exactly this means, but basically just if we have a value of sigma and x, sigma and mu that is, and we put in a value of x, we can find the value of the probability distribution for that mu and sigma at that value of x. Okay, I think this is going to be a bit more clear when we run this example. So let's run this one here. Okay, so this is kind of the shape of the normal distribution, right? So it kind of, some people call it the bell curve because it looks kind of like a bell. I think it kind of looks like a hat. And again, the probability of being between any two heights in this example is the area under this curve between those 2 points. So before we were talking about the area under a rectangle, now we're talking about the area under this curve. So for example, if we take height down to something really, really low, so basically the probability of being between 140 centimeters and 70 centimeters is basically a half. And the probability of being between any 2 numbers is something that we can calculate by finding the area underneath this curve. Okay, so that means that the probability of being exactly 170 centimeters, for example, so that's the same as what's the probability of being between 170 and 170? Well, that's exactly 0. So this kind of makes sense, hopefully. So basically the probability of being between 2 values that are quite close to the mean is actually still pretty big. So if you're just a little bit below 170 or just a bit above 170, there's still a decent chance of that happening. But if we move that over to the left, so to the right rather, so the probability of being the same distance apart at a much higher height is much smaller. Okay. So this means if we randomly select a person from the population, the probability that, for example, they're between 160 and 170 centimeters is going to be about 0.44. Okay, so just as before, we can generate random numbers that are drawn from this type of distribution. Okay, so here I'm going to set the mean of the distribution mu to be 170, the standard deviation sigma to be 6.5, and the number of random numbers to generate to be 20. And we can do just as before, random numbers equals np.random.normal, but this time we're going to pass the mean, mu, the standard deviation, or width, sigma, and the number of numbers to generate, n. So if we run this, here are 20 numbers normally distributed with mean 170 and standard deviation 6.5. Great, and we've got a bunch of numbers here. So these would be kind of simulating, if we went out into the population and randomly picked 20 people, here's some heights that we've collected. Great, and we're just explaining that in a bit more detail here. So just as before, we can make a histogram of these. So this time we've got the exact same parameters here, except this time we've got 2,000 random numbers that we're going to generate, and we're going to put them into an array, as before, into this variable. Make a new figure, plot a histogram of it, and put some axis labels. Great. Now, another little task here is just to go in, play with these numbers, increase these bins, just play around with this distribution and see what you get as a result. Okay, so one final distribution that we're going to talk about. Now this one is called the exponential distribution, and it's another example of a continuous probability distribution. Now this one is not quite as common as the normal distribution. I mean, you'll find the normal distribution absolutely everywhere. It's a really, really important one. This one is also pretty important, but it occurs in more specific situations, I'd say. So to describe the exponential distribution, we are going to briefly talk about nuclear decay or nuclear radioactive decay. So you may have, or you may not have heard of nuclear decay, but the situation is basically this. So you know that all matter is made up of atoms, and atoms are made up of a nucleus that sits in the middle and some electrons that orbit it, that whiz around outside the nucleus. Now the nucleus itself is made up of smaller things called protons and neutrons. Now protons are positively charged and neutrons have no charge. And what happens in radioactive decay, or in this particular type of radioactive decay, is that a neutron can turn into a proton and in the process emit an electron. And it does this because it's unstable. So basically, if it's got too many neutrons, it basically wants to get rid of them and turn one into a proton because it's just not basically stable in this type of nucleus. So the example here that we're talking about is carbon-14. Now carbon-14 is really, really important because it allows us to do something called radio or carbon radio dating. and I'll explain in a bit how we do that. But the situation is essentially this. The carbon nucleus has 6 protons and 8 neutrons. And what can happen is one of these 8 neutrons can turn into a proton, meaning there are 7 protons and 7 neutrons, meaning it's not carbon-14 anymore, it is nitrogen-14. And you've got a little kind of animation of what goes on there. So you start with this carbon atom with 6 protons, then one of the neutrons turns into a proton, giving you nitrogen, and an electron is released in the process. Now, nuclear decay is completely random. The only thing we can say about nuclear decay is that it has a set probability of happening in any given time period. Okay, so if we have an atom of carbon-14 and we leave it for 1 minute, the probability that it turns into nitrogen is constant, whether it's this minute or the next minute or the minute after. So it has this property that no matter what time you look at it, if you look at it and it's still carbon, it has a fixed probability of decaying into nitrogen in any given time interval. And we describe this by the half-life. So that means, and the half-life of carbon-14 is 5,700 years. So that, what that means is if we have lots and lots and lots of carbon nuclei, if we waited around for 5,700 years, we would expect approximately half of them will have decayed into nitrogen-14. So then if half of them have decayed, we wait another 5,700 years. Half of those that are left over will have decayed again. And then if we wait another 5,700 years, half of those that were left over would have decayed again. So you have this idea of kind of halving the number each 5,700 years. So what is the probability that a single nucleus decays in any given period of time? Well, that is described by the exponential distribution. We'll see in a second what exactly this distribution function means. But again, it's very similar to the normal distribution and the uniform distribution before. It's basically just a function, and we take the area under it, and that gives us the probability of decaying between 2 times. So let's just run this here. So this is what the exponential distribution looks like, and again, it has this kind of exponentially decaying shape to it, and the probability basically of a single atom of carbon decaying between any 2 times is given by the area under the curve between those 2 times. Okay, so we can see here, for example, if we take it down to 5,700, quite hard to get, but you can see that basically it's going to be, the area is exactly 0.5, because there's exactly a 50% chance that it decays between 0 and 5,700 years. Okay, so there's a couple of little exercises here for you. Can you find the probability that the carbon nucleus decays in the first 10,000 years? If we start with 500,000 atomic nuclei, how many do you expect will be left undecayed after 20,000 years? So you can use these little sliders to help you answer those questions. Have a think about it, see if you can come up with the answer. And just one quick thing that I wanted to mention here is that we can use this this radioisotope, carbon-14, to actually date objects in the past. So, for example, if you have a really, really old book that you think is maybe 5,000 years old, you can basically use this radioactive decay to tell fairly precisely how old this book is. And the way that you can do that is because all living things tend to have a constant proportion of all the carbon inside them that is this carbon-14 radioisotope. So if you know that at the moment that this thing died, so if it's a book, it's going to come from paper, which has come from trees. So basically at the moment that tree died, it had a constant amount of carbon-14 in it, or constant ratio of carbon-14. So if we measure the kind of radiation of this book, 5,000 years later, we can tell basically by the proportion of carbon-14 that's in the book now compared to nitrogen and other things. That'll basically tell us how much has decayed, what proportion has decayed, which means we can tell roughly how old it is, because we know that it decays at this kind of constant rate. Okay, so once again, another thing that we can do is generate some random numbers that are drawn from this exponential distribution. And yes, again, it's parameterized by, in this case, only one thing, which is this beta. So we have to provide it with a beta, and beta is related to the half-life by this here. So actually, I think that is actually divided by, if I'm not mistaken. So let's run this now. Okay, cool. So in this case, we have a beta that we're setting, which is the half-life divided by this thing, log 2. Doesn't matter too much exactly why that's the case, but we're going to generate 20 of these random numbers. And again, we're doing np.random.exponential. This time we're only passing one thing, which is the beta, and we want to get n of them. So you can see here we've generated some random numbers, so that's great. And once again, we can plot a histogram of them. Okay, so your final exercise again is just have a play around with all of these parameters, all of these things, see if you can kind of get to grips with it and understand it. And that is the end of this video. Thanks for watching.